Hi, my name is Harsha Patel, and this is Lab 3, Magnetic Field of a Bar Magnet. The goal of this lab was to determine magnetic moment of a bar magnet, to find the experimental magnitude and a simulated magnitude using a computational model of a magnitude at 45 degrees from the x-axis, and then compare these results. It was also to compare the measurement to the distance dependence that was predicted by the equations for on and off magnitude, on and off magnetic fields. So the results of this was that the magnetic dipole moment was calculated to be 3.42. The experimental value magnitude was 5.46 times 10 to the negative fifth power, and the simulated was 1.62 times 10 to the negative fifth power. Here are some of the fundamental principles of the lab. The Biot-Savart law is very important in understanding the calculations done. The magnetic field of a loop has the same shape as an on-axis magnetic field of a dipole, so that's given by the equations here. Magnetic dipole moment is given by this equation, mu equals I pi r squared. And then the magnetic field for section dl is as follows, with the constant times I times dl times the unit vector over r squared. And then some of the assumptions we made were that the bar magnet acts as a magnetic dipole, and this is assumed so that the Biot-Savart law can be applied. The experiment was conducted as follows. So the procedure was done as to compensate for magnetic north. We found the magnometer chip in our phone as depicted in the image on the top left, and then measured the on-axis magnetic field at varying values of magnetic field on x-axis, so at 20, 70, 120, etc. And then the measurement of off-axis magnetic field was done. So this measurement measured the distance between magnet and magnetometer when the magnitude of the net magnetic field was 100 T, and then we recorded the y component of the Earth's magnetic field, applied this measurement on the x-axis distance to the x and y direction. The magnetometer was placed here, as seen in the bottom left image, and then the magnetic field was measured at this distance in component form. So the system was the magnetometer, the surroundings were the bar magnet and the other surroundings, and the initial conditions was that the phone points to the magnetic north pole, and the magnet was placed at 0, 0, 0, the origin. Okay, so this Excel spreadsheet depicts the data analysis. So on the left is the on-axis measurements, on the right bottom is the off-axis. This graph depicts the model that as the distance from the magnet decreases, the magnetic field the magnitude of the magnetic field increases, and this is the equation given by our graph, which is important for our calculations later. So using that equation from before, we know that the slope is negative 3.85, found the value of ln k, which then gave us the value of k, which we plugged into our formulas down here, the given formulas, and we're able to calculate mu to equal 3.42. So the computer simulation is depicted here. The orange arrows are the magnetic field on the x-axis, the blue depict the magnetic field perpendicular to the x-axis, the pink is the magnetic field 45 degrees from the x-axis. So the simulation calculated our magnitude of the magnetic field at the 45 degrees angle from the x-axis to be 1.62 times 10 to the negative fifth, which is much smaller to the 5.46 times 10 to the negative fifth value that we experimentally calculated. So this is a stark difference that we found. So for the first what if we hadn't oriented the experiment to compensate for magnetic north and instead laid out the meter stick at some intermediate angle with respect to the Earth's magnetic field, the results would have changed because magnetic north would have contributed to the magnetic field measurements, and the X and Y components of the net magnetic fields would be different. And if we were to stick two identical magnets together end to end and run the experiment again, we would expect the measurements to differ because the magnitude of the magnetic field would almost double due to the combined fields, and the measured distances of each field would decrease due to the increased magnitude. Some sources of error include human error, such as magnetic fields nearby due to electronics, inconsistencies in phone placement, an uneven surface on which the phone was placed, and then, the visual for where something is measured is subjective, and sometimes the magnetometer would be inconsistent with its measurements.